Does this work?
Hi. Hello, everyone. Yeah, thank you very much for the introduction, and thank you very much for inviting me. I also enjoyed Neil's talk a lot, so I would love to have some time maybe at the end to actually contextualize it in the talk, or contextualize learning maybe in that diagram that you showed. I give it a shot. But yeah, so today I thought I'm going to talk about a problem that we. Oh, I'm sorry. If I go closer, that works? Okay, perfect. Let me try to breathe into this microphone. Yeah, if that works, then if there's no like how's this? I see like lots of light. How's this? No, also no good. Only if I do this. Okay, well, yeah. Let me turn this off again. Okay, let's try this. Then I don't have to lean like this. Okay, cool. So today I wanted to talk about long horizon manipulation problems or tasks that we are interested in my lab. And specifically, we've worked a lot on learning-based approaches towards this challenge and also using large language models. And yeah, so let's talk about long horizon planning, which is what we are interested in. Because that's what we would enable, that a robot comes into this beautiful kitchen like this one, right, and is tasked with a very high-level goal, such as cooking a meal, and of course then the robot needs to figure out the sequence of actions to achieve the goal. And I think planning every joint motor command to accomplish such a long horizon task is computationally infeasible, and it's helpful to abstract away some low-level details of the environment, such as the exact poses and geometries of the objects, and operate on the level of symbols instead, like whether the pot is on the stove or whether this microwave is closed or not. And then planning over or using the symbols to plan over a long horizon is called task planning, which Neil has already introduced earlier, and it has its root in early AI when researchers studied of how to give robots the ability to reason through symbols. And I think if you've seen the plenary yesterday, that also shed some light on the beginnings of this actually. And I don't think for this crowd I probably need to motivate task and motion planning, but let me go through this example because it's gonna come up later as well. So basically the point that I'm trying to make is that unfortunately task planning, although it's very useful because it helps us to compute on the level of symbols, ultimately we can't actually abstract away all the geometric details, right? So task planning by itself is really not enough. So for example, here, let's say this robot is supposed to pick this mug and put it into, from the dishwasher and then put it into the shelf. If we had a task planner, then it would come up with a very reasonable plan on the level of symbols at least, of picking up this mug from the dishwasher and then placing it directly into the cabinet. But unfortunately, if you basically try to do that on the robot, then basically this hand here in this particular example would actually collide with parts of the cabinet, which is unfortunately not great. So we really, as Neil also said, right, like we somehow need to communicate with this motion planner to understand whether a particular task plan is actually feasible or not geometrically or from the kinematics level of this robot. And so really what we would need is some information from the motion planner to help the task planner to understand that, oh, there's actually a better symbolic plan, like picking this mug from the dishwasher, placing it first on the counter, re-grasping the mug and then placing it in a slightly different way. And this really motivates this task and motion planning loop, right, to where the motion planner really has to communicate back to the task planner so that we get that kind of better symbolic plan. And so, of course, you're in the task and motion planning workshop, and Neil has also shown that there were so many workshops already, and obviously there are many very interesting foundational papers. Just demonstrating that task and motion planning has a very large interest in the communities. And here are just two videos of two state-of-the-art TAMP algorithms, which can perform also these types of long horizon tasks that we are interested in, such as grabbing objects outside of the workspace by using a hook as a tool to bring that object closer. That's for this logic geometric programming work. Or the other example is food preparation in the kitchen. And TAMP can find these very impressive long horizon planning solutions, or can find solutions to these problems. But the catch is that they are often extremely computationally expensive. And so for these particular works here, actually finding these solutions took several minutes. And as a result, often previous TAMP works are often demonstrated only in simulation, where you have like perfect information and time doesn't really matter so much, or computational efficiency doesn't matter, or it's like a highly controlled environment where nothing moves but whatever the robot moves. And so there are often no moving objects or external disturbances in when these methods are deployed and demonstrated on a real robot. And so one thing we were really wondering about in my lab is how can we do task and motion planning in the real world, where we can't just expect the real world to pause for several minutes, right, and wait until the robot is done computing. And so the focus of this task is really how to bring task and motion planning to the real world so that we can solve these long horizon tasks. And here's just an overview, very high level, of what we think like the important components are in such a system that brings task and motion planning really to the real world and deploys it. And a few things to note. Obviously, this is a very high level graph, but often task and motion planning works, they often like operate kind of on this top left half here of this graph, and are really interested and work on this interaction between the task and the motion planner. And we were really interested to go a little bit deeper and fill in all these dashed lines. And you see there's like a huge lump of perception like down there. And today I'm not going to talk about this. We've also done work there. It's a huge problem. I mean, there's a huge open problem on how to feed information perceptually into all of these different modules, but I'm not going to focus on this today. So we've done some work in that space. For example, I show you very briefly, without going into detail, this work on object-centric task and motion planning that we published at ICRA in 2020. And there we really wanted to look at the problem of how can we bring these TAMP methods into a dynamic real-world environment where things are basically pushed around by maybe a person, and not everything is basically controlled by the robot. So here is, again, example. We have the goal of the robot is basically to pick the small box, place it on the large box, but the problem is the small box is outside of the workspace. And so our approach, or the key contribution of this work, that we basically combine symbolic and geometric reasoning that uses object-centric Cartesian frames as a representation to plan and optimize over. And so in that case, we can actually do things like this, where you see what the robot is doing, and you see that objects are magically moving around. This is basically Toki, the first author of this work, that is like changing the environment, and the robot only has this plan that it computed over these object-centric Cartesian frames, and because of that representation, it can adapt to these changes of the environments, right? So it doesn't have to recompute this plan. It turns out also that actually, for some problems, optimizing over these relative pose variables can be much quicker than optimizing over joint configuration, which is what lots of related work has been doing. And this Tower of Hanoi problem here, for example, shows how these relative pose variables allow us to plan over really long horizons through decoupling the actions that these relative pose variables bring. And without decoupling these actions over time, this problem would be extremely difficult to solve, because the placement of the blocks early really determines what you can do later in the plan. And yeah, you see, like, they just took less than a second basically to compute. So this was really nice work. It has like beautiful math. You can look at the paper. It's wonderful. But one thing that we noticed is that actually there are lots of things that we still have to hand design in this particular work. And so this starts with like a PDDL domain, like this one for this particular problem. And this was just like a small problem, but you would basically need to do that to define that for the task planner, right? Like for all of the different tasks you may want to solve. And you also have to, so I didn't tell you anything about the technical details of this work, but basically this is the optimization problem that we're solving, that is inspired by Marc Toussaint's work, but changed basically for these relative pose variables. But basically the constraints that are inside of this optimization problem, they are all hand-defined, and they make a lot of assumptions about the types of objects that this robot is actually basically manipulating. Don't want to go into detail, but it would be very time-consuming to scale up the process of actually defining these optimization problems for all of the different tasks that we may, or primitives that we may want our robot to do over all of the different objects. And so we were really interested in trying to think about, like, okay, how can we scale up the number of manipulation primitives really that a robot could do and a task planner could basically plan over. And so we turned to learning to see, like, okay, there are all these methods out there that we and others have developed to actually learn manipulation skills. And so how can we, if we had these learned policies, let's say, for example, learned with this particular work that I'm also not going to talk about today, but pick any kind of work that learns manipulation skills, right? How can we then plan with these learned skills and actually sequence them together, maybe using a task planner? So you see now we basically took this diagram and we replaced the reactive controllers with learned policies. And there's now a gap basically in this plot, right? Like, so how can we plan with these learned policies is the question. So it's not just as simple as executing learned policies in a sequence, right? Because let's come back to this example that I explained at the very beginning, where the robot needs to pick up a mug from the dishwasher and place it upright in the cabinet. Okay, so let's say we can learn a policy with some method that picks up objects with 100% success rate. As we all know, this doesn't exist, but let's just make that assumption, and learn another policy that places objects into the cabinets with 100% success rates, right? So let's say we've learned these policies in some way, but executing them one after the other would not necessarily mean that the robot would actually succeed, since there are these geometric dependencies between these actions that the learned policy for picking up the mug doesn't take into account, right? So we need to figure out how to pick up the mug in a way that allows placing it later on into the cabinet. And before, with our handcrafted policies and this object-centric TAMP work, we used motion planning to reason about these geometric dependencies, and we kind of knew everything about the environment. But it's really not obvious how to do this with learned black box policies. And so in these, often for these learning these policies, right, like people use reinforcement learning, we did that as well, to train these individual policies. So you might think, why don't I use just reinforcement learning to also learn how to sequence these primitives together later on? And there are definitely papers out there that explore this route, and here are just 4 of them. And we see actually a problem with using RL on this high level, or there are some trade-offs here, especially for long horizon planning. And the reason for why maybe this is not such a great solution, or may not be optimal to pick, depending on the problem you're considering, is that there are actually infinitely many different long horizon tasks, and therefore there are infinitely many action sequences, each with their own set of geometric dependencies. that the long horizon policy would actually need to learn how to perform. And so what that means is that if you wanted to generalize over many different long horizon tasks, you have to train on an extremely large number of long horizon problems. And sample like RL is not exactly sample efficient, as you probably know, and it's really not a practical approach for large domains with many actions. And in fact, with the exception of the last paper here on the bottom right from Danny Dries, the RL policies in these papers are only capable of handling exactly one long horizon task. And then they can only generalize to different instances of the same long horizon task, right? So that's what they can do. And the one on the bottom right from Danny Dries and Marc Toussaint and all, this paper can actually generalize to other long horizon tasks, but to achieve this generalization, they require training on data collected from expert handcrafted policies. But our original motivation was really for using learned policies. In the first place, we wanted to overcome this bottleneck of actually hand designing, right? So, so that bottom right one doesn't really solve that problem either. Okay, so we don't want to use RL for actually sequencing, learning how to sequence these policies, right? Because of these shortcomings. So we really wanted to still exploit the strengths of task planning that can actually immediately, or of traditional task planning method that can actually immediately generalize to any long horizon task by reasoning over the logic of pre and post conditions. So we want to take advantage of the task planning's generalization ability, and the task planner will tell us which actions to perform and in what order. But what's missing is a way to do planning with the learned policies to handle the geometric constraints of the task. And so what we propose in this particular work that was published at ICRA in May is a sampling-based trajectory optimization method with policy value functions to realize TAMP with learned policies. Okay, so let's look more in detail at this particular approach. So we considered a problem where we are given a library of independently learned primitives. You can learn them in whatever way, right? So a sequence, and then we also assume there's a sequence of primitives to be executed coming from a symbolic task planner. In this particular example, right, like you've already seen that example before, the sequential manipulation task involves picking up the hook from the table and using it to pull an object closer that is initially beyond the robot's reach. And the challenge is that just greedily executing these primitives in a sequence fails to geometric dependencies. For example, if the robot picks up the hook in the most stable way it can at the center, it may not have 10 minutes. It may not have a reach to actually pull that object. And so the challenge is really that you have to take these action dependencies into account, and the task success here really requires reasoning over these long-term dependencies. Okay, so our core idea here is to cast this as a motion planning problem with learned primitives, to cast this motion planning problem with learned primitives as a maximization problem over the feasibility of long horizon task success. We show that this is equivalent to the product of Q function for each policy, for each primitive policy in this task plan. And so intuitively, this means that if earlier actions in the sequence are executed in a way that neglect downstream action dependencies, we might expect one of the downstream Q values to be low, and therefore the overall planning objective J that is plotted here will be low as well. And so how do we solve this? We solve this using sampling-based planning to find a trajectory where the Q values of all the primitive policies in the long horizon tasks are high. Okay, so here are three key components that we actually use in this approach. So we have the primitive policies that you train in whatever way you want. We used actually SAC, just an actor-critic approach. And then we also need dynamics models that predict the future states at which the Q functions of the other primitives will actually be evaluated. Yeah, so note that we actually train the primitives independently of each other. So it's also kind of an extendable library of primitives that we have here. And yeah, and then so we use SAC, and then the dynamics models are also learned. They are trained with the transition experience in the replay buffer collected over the course of training each primitive. And then we also use uncertainty quantification to basically, in a long horizon task, when a state actually ends up in something that the primitives hasn't been trained on, we can quantify that and actually downgrade basically the feasibility of that plan. Yeah, so then we have these dynamics models that are already described. Yeah, so in comparison to prior work, which includes model-based RL and traditional TAMP methods, our work can generalize to arbitrary long horizon task, produces plans quickly through the use of learned models, and promises better scaling to large libraries of primitives. Yeah, we evaluated this to baseline across 3 domains, each with 3 different tasks that constitute this unique set of action dependencies. And so here's again the hook reach that you've already seen for a while, right? And you see exactly what happens with the greedy method, picks up the hook, but then doesn't have enough reach with the hook, while our method takes this into account. Here we have another domain that is constrained packing, where basically this robot has to place all these objects on this little shelf without having them basically bump into each other. And we have this rearrangement push where the robot needs to basically put things into the shelf, again, also using the tool. And as you see, the greedy method also, again, picks up the hook in a way that makes it actually collide later. Right, so yeah, so basically if you're interested in more details on this work, feel free to read up on it. Basically the problem we considered are these sequential problems with action dependencies. Prior work trains primitives for solving very specific long horizon tasks, so they may have challenges in actually generalizing. And we train primitives independently and then maximize long horizon task success of a sequence. And the result is this, that we solve long horizon tasks that primitives have not been specifically trained on, actually. Right, so yeah, so with this, we basically now close this gap in this particular system, or in this kind of system overview of TAMP. But we still have this manually defined strip splitting. That is actually also quite a bit of work if you want to scale this up to maybe hundreds of different manipulation skills that your robot should be able to do. When we consider this problem, basically, of course, you're all aware of this. There are all these works that actually now use large language models to do planning over long horizons. So here are like 3 examples, all from Google. And what is interesting about them is that these in-context examples that you may provide to a large language model as a prompt, they provide kind of a more user-friendly way to actually define a task planning domain. And so we were thinking about like, okay, but is that something we could also do here to have a more potentially open the door for being more open-ended, a more open world with these large language models? Of course, the key question here, or probably you probably all tried ChatGPT at some point or the other, and you know it can basically output arbitrary garbage, right? So there has to be a way to actually verify these task plan that an LLM outputs. And so this was the key question we considered in this particular work. How can we use these language models to generate, but also to verify the plans for a task, especially with these complex geometric dependencies? So the particular problem that we considered here looks as follows. Again, a robot is equipped with a library of learned skills and a large language model. And it's given a brief description of the scene provided by some perception method. Again, I'm not talking about perception today. That's an entirely different problem. And then it's given a brief, then it's followed by an instruction of, for example, how would you fetch me any box from this table? And the robot's objective is to plan a sequence of actions that would satisfy the instruction if executed from the current state. And solving the task requires semantic and geometric reasoning. And there are myopic baselines that, like SECAN, for example, that basically inner monologue is another example, that basically end up in a cycle, right? If they don't consider geometric dependencies, they only execute things in a sequence, and so they might just end up in these particular loops. And another problem is we need to somehow verify that the robot has actually achieved a particular instruction, right? Is it done? And so the core idea in this work was to construct a plan and verify that it satisfies. The goal of this work again is to plan and verify with a large language model and understand if it actually satisfies the instruction prior to executing it. And so the way this works is like we basically have a step one in which the LLM actually infers a goal proposition from a language instruction. So, and also gets a scene description from a perception model. And then we use a hybrid planning method that combines the strengths of shooting and search-based planning by iterating first basically by generating useful skills or have the LLM basically output useful skills and then optimize a skill sequence with this algorithm that I just showed you that was called STEP. And then if the goal is satisfied, we basically return the plan. So how do the shooting-based method look like? We essentially have a method that queries the LLM and outputs an entire plan, and then we check if the goal is actually satisfied. And the pros are that it's very fast, it considers diverse solution, but the LLM plans are not often actually feasible. And we also have a search-based method that queries the LLM numerous times throughout a search. And the plans are likely to be feasible, but the cons is that it's computationally costly and there's minimal plan diversity. So in our work that is called text-to-motion, we actually combine these, and I'm totally out of time. But as you can probably imagine, this wouldn't have been published if we didn't have good results. So let me just show you again an example where we compare text-to-motion on the left for this constrained packing basically scenario, where in the middle we have a reactive baseline that is like Seiken or in a monologue, and on the right side as a baseline we have just a shooting-based method, which actually in simple scenarios also works quite well, but that actually fail when we have tasks that have like a partial affordance perception, where this shooting baseline basically has to find a plan and go through a very narrow set of options that it has a hard time finding. Okay, so I won't go through the detailed experimental results, so please feel free to actually look at this paper that is called Text-to-Motion. It's going to come out it's already on arXiv, and it will be published at Autonomous Robots. And the problem was to solve complex manipulation tasks expressed in language instructions. And prior work sequences skills myopically, where we now generate feasible plans and verify that they satisfy a goal proposition using this STEP method that I talked about in the middle of the talk. And the result is a method that uses these large language models to solve long horizon tasks with lifted goals and a partial affordance perception. So with that, you see now that we basically took this kind of traditional pipeline and ripped out a bunch of parts to try to scale it up to like larger domains. The large language models, I think, can offer new and more open-ended ways to plan robot actions, especially for long horizon tasks. And these are the two key insights. I have like this one slide that I took a picture from Neil's kind of mind map that he had in his talk in the very beginning, where he kind of categorized like all these fields, and he also put learning kind of like over here as a separate part. And I'm wondering, like, if I analyze this picture, I would probably take at least the things I've been talking about, probably in like different bubbles. They can probably fit in there because we still structure the problem in exactly the same way. So for task planning, for example, maybe I don't actually know. I have to think like more hard about like which bubble it would be. It would probably be more like a a heuristic search probably that we have done. And on the motion planning side, it was actually sampling based, where the objective function is this Q function or a value function, essentially, right? So I don't know if I would completely make like a different branch that is just learning, but maybe something to discuss. So thank you very much for your attention. These are my students who did all the work, actually. And yeah, I'm looking forward to questions if there is time, but I know I'm also out of time. Yeah.
Thank you, Jeannette. Let's take one quick question if anyone wants to come to the microphone quickly before we go on the coffee break.
How do you combine like the uncertainty and Q value and dynamics in the second one? Because it seems like combining this kind of learn the primitive with a test planner, you combine 3 different components, and how do you combine them together in one framework?
Yeah. I went through this pretty quickly. But yeah, so we basically have these learned primitives using, we used an actor critic method. So we get like a Q function. And we basically have a, when we train these Q function, we have like a replay buffer with experiences. And from those examples, we basically learned dynamics function. And so essentially what we do in the algorithm is we have like one primitive, we search like for the best possible way to execute this primitive. So it might be a particular graph, for example. And then we use the dynamics model to actually predict forward, like if we were to execute this, what would the next state be of the environment? And with that state, we look up the value in the Q function for the next primitives where we are supposed to execute according to our task plan. Does that make sense?
Yeah, that makes sense.
And I haven't explained the uncertainty quantification, but yeah, you could also use, again, like any kind of method that does that to understand like, oh, this Q function, right, like at this particular state, what's the support, right, like that we have from training? Is it like actually, has it ever been visited during training? If not, this Q value should have a very high uncertainty, and we take that into account for not avoiding to go through these types of out of distribution states.
Cool. Thank you very much. It's pretty good talk.
Thank you.
All right, I'm sure you have more questions, but we have a coffee break now, so you can take them offline, and let's thank our speaker again.
Thank you.
And we'll be back at the hour.